Hello and welcome everyone. Thank you for joining us. Welcome to today's webinar, What's New in ENVI Deep Learning 1.2. My name is JP Metcalf and I'm a solutions engineer over at L3 Harris Geospatial Solutions. Just a couple quick things before we get started. Everybody online is muted. So if you have any questions at any point during the webinar, make sure to put them into the questions and answer chat box, and then we'll get to those towards the end. We are recording this webinar, and I'll have it up on our website at l3harrisgeospatial.com in the next couple of days. We'll also email you a link to the recording as well as the slide deck that we're presenting today, which you are also welcome to share with colleagues that were not able to attend. And with that, I'll send it over to Zach Norman.
Thanks for the introduction, JP. Before we get into content today real quick, just want to share with everybody kind of our contact information. So apart from seeing our lovely faces here on video, there's some nice pictures of us. There's emails. So if you guys have questions that aren't answered during the webinar, feel free to reach out to us or your account manager or whoever you talk to in our group, and they'll usually find their way towards us. So like I said, just for transparency, if you got questions, feel free to send emails. Just to kind of reiterate, since this is kind of our first Zoom webinar for what's new, potentially for some people, there is a chat functionality and there's Q&A. If you can put your questions in Q&A, that would be great. I try to keep an eye on that as we're going through. If there's a lot of chat, it's kind of hard to follow if something does come up. So with that, let's go ahead and talk about what we're going to be talking about today. Here's a snapshot of the agenda. We're going to do a very quick kind of review recap of ENVI Deep Learning. Kind of the expectation is that you're at least familiar with ENVI and what we do kind of as an organization. If you don't, check out our website where you can learn some more there. And then we're going to talk about what object detection is. And we're going to have kind of a workflow focused approach going through some of the new features that have been added to the deep learning module to support object detection. And then at the end, we're going to wrap up with some use cases and comparing object detection versus what's in ENVI Deep Learning today, kind of side by side. So with that, actually one more thing. We've got 30 minutes today for time. We will use the full 30 minutes. Depending on how many questions we've got, we might go a few minutes over. So if you have to hop off at the end and your question didn't get answered, just like our normal webinars, we usually go through all the questions and we'll send out kind of an FAQ with anything that people tend to be asking a lot. So with that, let's jump on in. So as I said, we're going to start with a little review of ENVI Deep Learning. So ENVI Deep Learning, hopefully everybody is familiar with. It's a module add-on for ENVI where we wrap TensorFlow and Keras in an easy to use, friendly user interface with an ENVI that lets you generate deep learning models without needing to program or write any code whatsoever. So the workflow that we've got implemented within ENVI today for deep learning is creating training data, generating models, and evaluating the performance of those models, which is the larger part of the deep learning workflow that we're going to walk through for object detection. And with the capabilities in deep learning, we're classifying imageries and we're using semantic segmentation, pixel classification. You'll hear me use both of those terms kind of interchangeably throughout today's webinar. But you can also extract linear features. And one of the nice things about pairing ENVI with deep learning is ENVI has support for many different data formats and modalities of data. So with the two examples down in the lower right, one's using optical imagery to assess building damage after a disaster. And then in the lower right, we're using SAR data with deep learning to extract floodwaters. So it doesn't have to be just optical imagery. It can be SAR. It can be derived products from point clouds as well. So we'll talk about that a little bit more with some of our object detection use cases. So with that, let's talk about, I keep getting ahead of myself with this slide. Before we get too far in this, with the next release of ENVI Deep Learning, being 1.2, you'll need the latest version of ENVI, which is 5.6.1. And then you have to have an NVIDIA GPU. That is a TensorFlow requirement. So along with this, CUDA 11 is not necessarily required, it's supported. So if you've got the latest versions of drivers and CUDA, you should be all set and good to go. So we'll probably spend a little bit more time talking about that at some point. We just want to be crystal clear. If you've never worked with deep learning before, this is a requirement for ENVI Deep Learning. All right, so now let's talk about object detection and what we've added to this release. So there's a couple different types of deep learning, actually more than a couple, there's a lot. This is a image that I got from a blog post. You'll see the URL to it down in the lower left. So just starting in the top right with semantic segmentation or pixel classification, that's what we've had already in ENVI Deep Learning. So basically you have an image, you'll process that with a model, and you get a mask out or a traditional ENVI classification image. And this is similar to what we have today in ENVI using traditional spectral processing like spectral angle mapper or Mahalanobis distance. You basically get a pixel map with a lookup of what each pixel belongs to for a material or type of feature or something like that. And so what's been added to the deep learning module is object detection. So instead of a pixel map, you actually get geometry for your features out. So you get a bounding box that covers the extent. One of the advantages of this is that it allows for different features to overlap with one another. Whereas if you have semantic segmentation, if your objects are touching, you're going to get kind of one clump of pixels that's going to be turned into one feature if you're vectorizing your data. So instance segmentation is a more information-rich version of object detection where you get polygons for your features. One of the reasons we stuck with object detection instead of instance segmentation is object detection is a lot easier to label data for. You know, a bounding box is click or drag or just 2 clicks for the corners instead of having some complex polygon. So that's one of our main driving forces for why we started with object detection. But with that, let's go ahead and jump into some of the new capabilities that have been added to ENVI Deep Learning to support this. First place that we're going to start is the Toolbox. So this is the new Toolbox for ENVI Deep Learning 1.2. There's a couple little areas to it. It's separated by pixel segmentation and object detection. And then our 2 universal tools, the Deep Learning Guide Map and the Deep Learning Labeling Tool, have both been updated for supporting object detection as well. So there's a screenshot of the Deep Learning Guide Map in the top right there, which shows pixel segmentation and object detection as 2 paths that you can click your way through if you're so inclined. But you know, from a deep learning workflow perspective, and taking a step back to the slide I showed just a few minutes ago, our deep learning workflow consists of labeling data, generating classifiers, and evaluating results. So the first step of that workflow is labeling data. So with that, we're going to start with the labeling tool that's a part of ENVI Deep Learning. So starting over on the left side of this slide, when you're creating a project with the labeling tool in ENVI Deep Learning, you now have the option to pick if you're using object detection or pixel classification. So these are 2 fundamentally different modes for the labeling tool. If you're using object detection, then you're drawing bounding boxes like the video shows on the right. If you're using pixel classification, then you can draw points, polylines, or polygons, and basically you're identifying the pixels in an image that represent the features that you're interested in. And just as a quick refresher, if you've never used the labeling tool before, the labeling tool manages your classes in your data for you, and it allows you to train a classifier with a single click, apart from all of the clicking you do to label your data. So it just kind of organizes everything and manages the data so that you don't have to, and provides that automation framework for generating classifiers, so you don't have to write any code or use the ENVI modeler or something like that. So once you've labeled your data, that's where you're going to get to training a classifier. And before we talk too much about how to train object detectors, I just wanted to show kind of side by side what we have in ENVI Deep Learning today and what training object detections look like. So there's fewer parameters, we've streamlined a few things, and there's not as many knobs to turn with object detection. So overall, creating a classifier is simpler, I would say. And so taking a closer look at what's part of training object detection classifiers. I'm not going to go through all the details here. You'll get a copy of the slides. You can read all of the text later if you'd like. There's three things that I want to make sure to call out. So the first one up at the very top is when you're training an object detection model, you're going to specify the name of the model and optionally a description. If you've used ENVI Deep Learning before, you used to have to create or initialize a model and then train it as two distinct steps. That's not a part of the object detection workflow. It's all bundled up at once, and we always use pre-trained weights as a starting point, which helps your models converge faster and perform better. One of the other important things I want to call out here is our third kind of red, or our second red box from the top, which is pad small features. We're going to talk about this in a little bit more detail towards the end of the presentation, but there is a minimum size for features that you can use with object detection. That threshold is 25 pixels using ENVI Deep Learning. And if you enable this parameter, which is on by default, if you have an object that's say 20 or 15 pixels, you'll get 5 or 10 pixels added as a buffer around it, just so you can use your labels with deep learning. But like I said, we'll talk about that a little bit more towards the end. Lastly, and probably one of the biggest differences between object detection and what's previously been in deep learning with pixel classifiers is how you train. For object detection, you just have to specify the number of epochs, the fraction of your data that you want to use for training, and then optionally, if you've got a bunch of empty patches in your images where there are no samples, a fraction of those to go into the training pool as well. So when you're training with UNet style architectures, you'd have to specify the patches per epoch, which gets really hard if you have rare features or a lot of data to train on. You don't know exactly what to set that to. So we automatically calculate that behind the scenes for you. So really it's just the number of epochs that you need to change, and you can leave just about everything else at default. So once you have specified your parameters, which like I said, there's not too many knobs to turn here. About the only thing you'll really be doing is specifying your rasters that you're going to use for training or validation. And if you're using the labeling tool, that's done automatically for you. But once you get to training, just like we've had in the past with deep learning, you'll have metrics and live progress for how the model is performing reported through TensorBoard. So if you're not familiar with TensorBoard, it's a web application that allows you to see the performance of neural networks during and after training. For object detection, we just report the loss. And we'll talk about this in a little bit more detail as well. But if your loss is around a value of 0.2, it means it's converging well, and you should have pretty good performance. Like I said, we'll touch on that again towards the end of the presentation. So one of the advantages of TensorBoard is seeing everything in real time. Means if you notice a problem or notice that your model isn't converging, you can stop training instead of having to wait, a couple of hours or longer, depending on how much data you have. So, just recapping on our workflow here, we talked about how to label data, some of the parameters for training. TensorBoard is what you'll use to monitor progress during training. And the next step is going to be looking at the outputs when you classify imagery and how to kind of work with that and evaluate performance. So first step there is viewing the results. So when you're using object detection in ENVI Deep Learning, the output is a vector. So you get a shape file with 3 different attributes: the ID of the class, the name of the class, and then the confidence value associated with the detect. Just an important thing to note, we use shape files if your image is georeferenced or not. So there's a little bit of magic in ENVI that lets you use a vector file with a data set that is just pixel coordinates, so there's no map information associated with it. So everything still lines up and it works as expected. So people that might always use commercially available satellite data, that's not every data source, so it's an important use case that we made sure to cover. An important thing to note here is if you look at the screenshot on the left, you'll see that the boxes are all bright lime green. So when you display the vector file as outputs from object detection, there's information that ENVI uses to properly set the color and display of different bounding boxes. So if you have a multi-class object detection model, you'll see the different classes be represented accordingly by the colors that you labeled them. You'll see that a little bit later once we get into our examples towards the end of the presentation. But one of the things that you might be thinking is if you're looking at your results and you see that confidence value as an attribute, what's one of the ways that you can explore that in a little bit more detail? So the first thing that you'd probably end up doing, especially if you just created a model, you're viewing your first results, is you want to know a little bit more about how well your model's performing. So a little fun fact, if you didn't know it, within ENVI, if you're viewing a vector, you can add a color table to an attribute on that vector file. So here, I've got a fancy blue-red color table applied to the confidence value, same data set from the last slide. Lets you quickly visualize where there's detects with low confidence. Maybe you can identify some of the features that your model's not learning too well, so you can add more to your training pool. And in addition to this is a great tool to help you with figuring out what you can do to automatically clean up your results. So when I'm talking about cleaning up results is you're probably going to have some false positives in here that you need to get rid of. So if you need to clean up your data set, we have two different ways that you can do that within ENVI. The first one is there's a tool called post-process classification vector, which lets you adjust the threshold for confidence. You can use an intersection over union threshold, or IOU, to filter out boxes that are overlapping with one another. And then we have a third custom filter where if you have small boxes fully contained within larger boxes, and that should not be the case, you can filter out those as well. So in that screenshot, you'll see automated cleanup results before and after. This is with a model that I didn't train too much to have a nice demonstration of this capability. You'll see the results in a little bit more detail here in a few minutes. The other thing that you can do is directly within ENVI, and I didn't know this for a long time, is that you can edit and create vector files from ENVI. So if you are viewing a shape file that's got your results, up in the toolbar, there's this little vectors drop down, and you can use edit vector to go through and select different entities and delete them. So it's a great way to quickly clean up results or fine tune where boxes might be overlapping a little bit, or there might be two boxes for a single feature. It makes it very easy to adjust. Taking it to the next step here. So that kind of covers our workflow and the high level tools that you'll use within the ENVI Deep Learning 1.2 release for training, viewing progress during training, classifying your results, and interacting with the outputs. One of the things I always like to call out, and not to scare you away if you're not a programmer, but if you are a programmer, we almost always add ENVI API for buttons and tools that you can use within the ENVI interface. So here on the left, I just have a screenshot of some IDL code that's used for pre-processing data, adding a custom stretch before it gets passed along to deep learning. Over on the right is just showing how easy it is to actually generate a classifier via the API. So it's pretty much copy and paste from our documentation. The hardest part there is data discovery and making sure you separate everything correctly into your training and validation data sets. So like I said, not for everybody, but if you are a programmer, you can access ENVI Deep Learning programmatically, but you don't need to in order to use the tools. Now, one other thing I wanted to make sure to spend a little bit of time on before we get to our examples is talking about creating custom training data. So without needing to program, there's some tools within ENVI that let you create existing vector files you have to ROIs, and you can use ROIs and annotations directly with object detection. But say, for example, if you have data that's a different format, or maybe some customized GeoJSON, or there are points that you need to turn into polygons. I just wanted to show a couple of snippets. So over on the left is using the ENVI ROI API for creating polygons. So that's turning a point into a square, basically. and then you can use that as directly with object detection. And then over on the right is a more verbose and in-depth example. Advanced usage over on the left is a great place to start. So I just wanted to demonstrate that if you've got kind of a different flavor of how your labels are stored, there's plenty of ways that you can get those into ENVI Deep Learning. You don't need to program to use this though. So there are some out-of-the-box tools. This is just for customization for things that might not meet your out-of-the-box needs. So with this, sorry, I forgot about this slide. One more thing. So if you are creating your own training data, one of the things that you're going to want to do is make sure that your training data is correct. So believe it or not, I even mess this up sometimes if I'm programmatically creating training data, where after you create an object detection raster for use with training, you'll want to double check that the labels for your features are correct. So there's a view object detection raster labels tool within ENVI. You need to use this if you want to see the labels that are passed on to deep learning. And one thing I want to call out is there's an ENVI bug that you may encounter if you're using this tool. It's going to be fixed in the next ENVI release. We are aware of it. I just wanted to call that out because I'm advertising this functionality, but this is more for people who are programming and creating their own training data, or just want to double check that everything looks kind of as it should before you start training. So, all right, from here, we're going to quickly run through some examples. Quick little time check here. We'll probably finish up most of the content in about 5 or 6 minutes, and then we'll have some time for questions. Like I said, we might go a few minutes over depending on how many questions we've got. So first example I want to just walk through here real quick is aircraft detection. So one of the things that I may or may not have said is that with object detection, you can use any number of bands within ENVI. So this is using worldview panchromatic data, where we have several different types of aircraft here. There's 2 specific types, which are the green boxes and the black boxes. And then there's a blue kind of catch-all class for aircraft, and then yellow represents helicopters. So object detection in ENVI is multi-class. You can use single band data if you want. And quickly moving on here to another example, ship detection. So using kind of more traditional remote sensing data of optical, this is actually 4-band VNear data. So this is planet scope, surface reflectance, and we're doing ship detection. So earlier I made a comment about the minimum size for bounding boxes. If you actually look at some of the ships kind of over on the left side, in the lower left quadrant of this image, you'll see that the bounding boxes are quite a bit bigger than the ships. That's because when I was preparing my training data, I turned some points into bounding boxes and I made them bigger on purpose so that I'd be above the 25 pixel threshold. So 4-band data set. So like I said, it doesn't have to be 3-band. And just to reiterate that a little bit more, this is not the most exciting example here, but ship detection using SAR imagery. So just to call out, you could use SAR data, doesn't have to be panchromatic. This SAR data set specifically, it's a derived intensity product that's been byte scaled and normalized. So it's something that you can open up. It's not the raw SAR data. It's in a traditional image format and projected. So you can see one ship in the top left, and then there's another one kind of in the lower right. Ship detection is not really a hard problem to solve with deep learning because the water is usually pretty dark and ships pop out kind of like the one in the top left. They're little bright specks against a dark background. So next example, just to walk through is turn arrows. So different classes of arrows, whether they're straight, left, or right. This is just using RGB aerial imagery and just trying to illustrate that multi-class with object detection as well. And then our last example here is vehicle detection. So different types of vehicles in an urban setting on the left and over on the highway on the right. As I mentioned before about the bounding boxes being colored the same as your classes when you open up the outputs from ENVI Deep Learning. So you'll see the different colored boxes, and that happens by default after you classify an image and view the results. So makes it a lot easier than having to look at the table of attributes to manually identify which thing you see in the vector file is class. So, all right. So with that, I've got this slide, and then we'll get to kind of Q&A. One of the things that when I was talking with JP on Monday is prepping for the webinar that I thought would be really good to add here is kind of a side-by-side comparison to pixel classification or UNet type architectures and object detection within ENVI Deep Learning. So I'm not going to spend time talking about everything here. But what I do want to focus on a little bit is the amount of training, so epochs for training. So if you're using object detection, you're going to have to train a little bit longer or a lot longer, depending on the type of feature that you're going after and how hard it is or easy it is to see. So I recommend starting with at least 60 or 75 epochs when you're using object detection models. And like I said before, the loss value during training should be about 0.2 or less than that. If your loss value is around 0.5, you're probably going to have some bad or not great results with lots of random boxes and false positives. Even if that loss value is a little bit higher, you should still at least see some positive detects of your feature that show that deep learning is kind of starting to identify and really learn what represents the objects that you're interested in. Now, if you're using pixel classification, you can sometimes get away with 15 or 20 epochs. For models with a lot of data, I would probably do between 35 and 50 with pixel classification, just depending on how hard the feature is to identify and how many different kind of representations of it there are. And one of the things that I kind of think about, this is a personal observation here, is when you're using pixel classification, a fundamental difference between that and object detection is that every single pixel is a training sample. So if you have an image that's, say, 1,000 by 1,000, that's 1,000,000 pixels that deep learning can learn from. Whereas with object detection, you have to manually specify every bounding box. So, there's going to be fewer bounding boxes than there are pixels. So that's part of why I would say it takes a little bit longer to train. And in addition to that, object detection is giving you a bounding box and a class for that bounding box. So there's two different things that the network has to learn, and it can just take longer. So last thing I want to focus on here is the size of features. So with object detection, your minimum size of features, as I've said before, is about 25 pixels across. And then the maximum size is going to be limited by your patch size. So the amount of data that we feed into deep learning at a time is 400 by 400 pixels, which is an upper limit. So if you have features that are larger than that, then you're going to want to downsample your data to use that with object detection, or maybe try your luck with pixel classification. Even then, if your features are that large, I would always recommend downsampling your data, which will help you process and train a lot faster because there will be a lot less data to work with. The last thing that I would say, and this is more a recommendation, you can feel free to try this if you want, but from a relative size of features that you might be training for, I would recommend not to train a model with classes that vary too much in size. Meaning you don't want to be trying to detect like parking lots and cars at the same time. It's probably better to have a model that's just parking lots and just cars and maybe collating the results in some way. Part of that is thinking about cleanup. If you have false positives or just lots of little boxes within big boxes, could make cleanup a little bit tricky. So with that, I think we've kind of wrapped it up. So if you have questions, like I said, use the Q&A little section in the Zoom webinar toolbar there to ask questions, and I'll turn it back over to JP.
Amazing. Thanks, Zach, for the presentation on our new deep learning capabilities. We have had quite a few good questions come in. I think the first one that we have is from Sam, and it's, do the vector results have a specified schema? And if so, are they populated with the image metadata?
Yeah, so good question. Actually, I can go back a couple slides. So the vector results, it's a shapefile that's actually generated. So you can convert that to GeoJSON or some other type of vector data if you need to. And it always has 3 attributes: the class ID, class name, and confidence. That vector file does not have any information about the source image that it came from. It just exists standalone, independent from the imagery.
Fantastic. Another one that is from Cody is the 25 pixel minimum. Is that flexible?
It is not. So that's a limit with our architecture that we picked, and it's something that we're pretty much aware of from the beginning. 25 pixel minimum. So far, we haven't had any cases where we've had a problem with it. Like I said, there's a parameter during training that will automatically pad your small features to be 25 pixels if they're smaller than that. So it'll add just a little bit of a buffer. The other way I think about it is if your features are too much smaller than that, then they start to get a little bit harder for you to see as well. Which if it's harder for you to see, it's probably going to be a little bit harder for deep learning to detect too.
Great. Another one is, and I find this one interesting, is does ENVI Deep Learning have a capability regarding object detection of video files? Can we do that in time series?
That's a great question. So we don't, so just talking about ENVI in general, ENVI has kind of some basic support for being able to view and work with video. If I remember correctly, I think you can open up a video file and create a time series. If you have a time series, you could apply object detection to that time series and get results for each frame. But just to be very clear, that's not the same as object tracking, if that's what kind of the reason for asking about video is. Object detection in deep learning is not something for tracking features that you might see in a video frame.
Detecting. And a question that we had earlier is, back in the early slides, what was the source of the image that was used to label the ships?
Oh, so for ship detection, there were 2 of them.
In the very beginning.
The very beginning.
That one.
This image.
Mm-hmm.
Great question. I can't remember if this was Demos data. It may have been, it was either Demos or Worldview. It would have been Worldview 2 or 3. I can't remember. I can't remember exactly.
Okay, one more before we have to get out of here. There is a question from Minsu. Does your features, for instance, aircraft features, handle various rotations to identify aircraft with any random direction?
Yes, correct. So I'll answer that in kind of 2 parts here. Let me go back into presentation mode so this is a little bit easier to see. So for both types of deep learning that we have, and you should be able to see my mouse. If you look at the screenshot on the right for object detection, we have augment scale and augment rotation. And if you look over on the left for our units as well, we also have augment scale and augment rotation. So what that means is during training, we'll randomly adjust or zoom in a little bit on your patches, or potentially rotate them up to 0 to 360 degrees. So the models that are generated should be rotation independent. So if you have like an airplane facing north-south, and that's all you train on, you should be able to detect airplanes that are facing like east-west or northeast southwest, if I get that right. So yeah, but orientation of features does not matter, and we use augmentation during training to help make the models a little bit robust to that as well.
Great. With that, we're coming up on time, so let's wrap things up. We appreciate everybody's attention on the line, and thank you again, Zach. Again, if there's any questions that we didn't get to, please email us. Our emails are on screen right now. And just a reminder that the recording of this webinar and the slides will be emailed to you in the next couple of days. It'll also be available on our website at www.l3harrisgeospatial.com. And we encourage you to share it with your colleagues that weren't able to attend. Thank you, everyone, and have a great rest of your day.
Yeah, thanks, everyone. We'll see you later.